In this video, we're going to take a look at an algorithm called topological sorting. So topological sorting algorithm basically sorts the directed graph in a linear ordering where each vertex, right, where each node uv from vertex u or node u to point to vertex v, the ordering is going to be u, node u, right, the vertex u comes before vertex v, right? And then there are a couple applications when we use topological sort. For example, school system, right? So let's say we were to take calculus 3. If we were to take calculus 3, we have to take calculus 2, right? And that's the prerequisite for calculus 3. And if we were to take calculus 2, we have to take calculus 1. And that's the prerequisite for calculus 2. And if we were to take calculus 1, we probably have to take pre-calculus 12, right? So we want to know the prerequisites for the course that we want to take. So we will use topological sort to sort the each course with its prerequisites, right? So in this case, we have a another use case, for example, task scheduling system. For example, if we were to figure out which task to perform first, right? Because some tasks we need to we have other tasks complete first before we have to complete this task. So for example, if I were to complete task 3, we have to complete task 2. And to complete task 2, we have to complete task 1. So we sort the graph using topological sorting so that we know which task to perform first. And same thing for the school system. We sort the graph so that we know which course we have to perform to complete first before we take the desired course, right? Let's say we were to take calculus 3. If we were to sort the graph, we know that we had to take calculus pre-calculus 12, right? And also then we have to take calculus 1, then we take calculus 2, and then we take calculus 3 to reach to that point, right? So we need to know the path. By performing topological sort, we can know the path to get to a certain course. So for performing topological sorting, there are a couple conditions. So one of them is that there cannot be directed cycles, right? So here you can see we have a cyclic graph where we have a cycle in the graph, and you can see that to complete course 0, we have to complete course 2. And to complete course 2, you have to complete course 1, and you have to complete course 0 to complete course 1. So you can see there's a cycle. And we cannot perform topological sort if there is a cycle, right? And if there is a acyclic graph, we call it directed acyclic graph. That means that there is no cycle. So you can see node 0, there's no prerequisite. So that can be the entry point, right? So we take that as a start. And then we have to complete task 1, because in order to complete task 1, you have to complete task 0. And then to complete task 2, you have to complete both 0 and 1. So there are at least one topological sorting version of every directed acyclic graph. You can go with different ordering, but at the end we have a sorted topological sorting of the acyclic graph. So there are many ways of implementing it. The algorithm that we're going to take a look at today is going to be Kahn's algorithm, and then you can also use depth first search to perform topological sorting. So like I said earlier, there's at least one topological sorting for every directed acyclic graph. Let's take a look at an example. Here you can see we have a valid topological sorting orders. So here you can see we have a graph, and to perform topological sorting, one way is we can do a top to bottom, top down, right? We can get all the graph that has no prerequisites, right? The courses that has no prerequisites, to add it to the order first, right? Node 1, node 2, node 3, and then node 4, because in order to do node 4, you have to complete node 1, node 2, node 3. Then you can complete either node 5, node 6, and node 7. So node 5, node 6, node 7. And after you finish node 4, and after you finish node 5, node 6, node 7, you can complete node 8. So we can sort this way, right? We can say 1, 2, 3, 4, 5, 6, 7, 8. We can do it this way, or we can do it bottom to top, right? We can do the opposite way. We can do 3, 2, 1 because they don't have any prerequisites. So we can do them in any order. We can also do them in 2, 3, 1, right? Because they don't have any prerequisites. and then 4, and then 6, 7, 5, or 7, 6, 5, and then 8, right? So there's many ways you can perform topological sorting. And then let me take a look at, let's take a look at another example, right? So here you can see we have a graph, right? So a cyclic graph, and then we can perform topological sortings with all those valid, all those orders are valid. So you can see we have 4, 2, 3, 0, 1, 4, 2, 3, 0, 1, right? We can do it this way, or we can do it 4, 3, 2, 0, 1, or 4, 3, 2, 1, 1, 0, or 4, 2, 3, 1, 1, 0, right? And there's many ways that we can perform the orders of the topological sorts are many, at least one, right? So these are all valid because this has no prerequisite, and in order to take 2 and 3, you have to take 4, and to take 0 and 1, you have to to take 0 you had to take 2, and to take 1 you had to take 2 and 3, right? So let's take a look at the Kahn's algorithm, right? So the approach to the Kahn's algorithms is that we want to get all the nodes with no incoming edges onto the hash set. Then we will declare a result list that will basically takes the sorted elements, and at the end we're just going to return this sorted list, right? So here you can see basically the approach is that while the hash set is not empty, we're just going to take a node in from the hash set and then add in to the result list. Then for each M, right, all the edges, all the nodes that are connected to N, we're going to remove that edge, we're going to remove that connection, and if M does not have any incoming edges, then we're going to add M to the hash set. So if there's no incoming connections to the M, right, node M, then we're just going to add it to the hash set, and if graphs still have edges, then we're going to return false. At the end, we're just going to return a result if it's not false. So the goal is that we have a topological sort, and here's, you can see we're doing an example, right? So here we have a result list that store all the nodes with no edges at all, right? And we basically, at the end, we just return this result list because this is just a sorted graph, right? So here we have a hash set. We basically add all the nodes that with no incoming edges onto the hash set, so A and G, right? Then what we do is we basically remove that connection, right? We know that A is pointing to B. Then we're going to remove that connection, AB, we're going to remove that, and then we're just going to add A onto the result list because we know that it doesn't matter which one, either you can add A or G, but we're just going to add A onto the result list. And then basically because that there is no connection here, there's no edges, we cut this edge, we cut this connection. So now we know that B has no incoming edges, right? When I say incoming edges, that means that there's no incoming connections. Like there's no node that is going to point to B. There is always B pointing to other nodes, but there's no nodes to point to B. So we add B onto it because we delete this connection. Then what we do is that we are going to get the C out, and then we know that the C has no incoming edges, so we're going to remove this edge, right? We're removing this edge. We add G onto the result list. And then what we're going to do is we know that D, right, D has no incoming edges now because we delete this connection. Then we're going to add D onto the hash set. And then what we're going to do is we're going to remove all the connections that B has, C, E, and D, right? Then we're going to add nodes that has no incoming edges, no incoming connection, like C, E, and D, where we already add D already, so we don't have to. So we're going to add those nodes onto the hash set. And then we're going to get B onto the result because B now has no edges, right? All the edges that B has is gone. Now we have D, right? So when we do D, we also have to remove all the connections that D has. Now D has a connection with E, now we remove that. And now now D has no connections. Now we're just going to add D onto the result list. And then CE, so now we deal with C. C has a connection with E, now we remove the connection on C. And now we have E. E has a connection with F, then we just remove that connection, all the connection that E has. And then we know that there's F, So F has no connection, right? So we basically pretty much remove all the connection that F has. Then we're going to add F onto the result list and remove that element off of the hash set. So basically, this is how we use topological sorting to perform sorting on a acyclic graph, right? So what we're going to do now is we're just going to do a Leetcode problem called course schedule. So there are total of number of courses that you have to take labeled from 0 to num courses -1. You're given an array of prerequisites where prerequisite I is equal to A at I and B at I. So index indicates that you must take course B at I first if you want to take course at A at I. So for example, 0, 1. So indicates that you have to take course 0. To take course 0, you have to first take course 1, right? So the goal is we want to return true if you can finish all the courses, otherwise return false, right? So basically we want to make sure that we're doing topological sorting, right? To do a topological sorting on an acyclic graph. If we realize that this is not an acyclic graph, just like what we talked about before, right? If it's not an acyclic graph, then what we're going to do is we're going to return false, right? If there's still edges remaining, then we're going to return false, right? So here you can see we have a number of courses. In this case, we have 2 courses. So if we only have 2 courses, then there's going to be true, right? Because we can take this course. To take course 1, we have to take. To take course 0, actually, we have to first. My bad. So if we were to take course 1, we have to first take course 0, right? So there are going to be a total of 2 courses. And the goal is that we want to make sure that we can be able to finish all courses, right? So in this case, we're just going to return true. And now here you can see we have another example where we have a cyclic graph where we have a node 1, right? And node 1, in order to take node 1, we have to take node 0. And to take node 0, we have to take node 1. So you can see we have this cycle in the graph, right? Where we are to take this course, you have to take this course, and to take this course, you have to take this course. So it doesn't really make any sense. So we're just going to return false. So let's say we have more example like this, where we have 0, 1, 1, 2. So to take course 0, you have to take course 1. And to take course 1, you have to take course 2, right? So let's draw this out. You have to take course 0, and to take course 0, you have to take course 1. And to take course 1, you have to take course 2. So can you complete all the courses? And the answer is yes, right? It's true, right? To execute task 1, task 0 needs to be finished first. And similarly, task 1 needs to be finished before 2. So we can return true. Now let's take a look at another example where we have 0, 1, 1, 2, 2, 0. The reason why we return false is because let's say we have 0, right? In order to take course 0, we have to take course 1. And to take course 1, we have to take course 2. And to take course 2, we have to take course 0. So you can see there's a cycle in the graph. So in this case, we have false. And then here you can see we have more examples. Let's say if we were to take course 2, we had to take course 5. And if we were to take course 5, if we were to take course 0, we had to take course 5. Okay, and if we were to take course 0, we had to take course, we also had to take course 4. And to take course 1, we also had to take course 4. So right here. And to take course 3, we had to take course 2. And to take course 1, we had to take course 3. So in this case, to take course 1, right, we had to take course 3. In this case, we can just return true because in this case, we have no cycle, right? We can do course 5 first, then course 2, then course 3, then course 1 and course 4, and then course 0, right? Because you need to take course 4 you need to take course 5 and to course 4 to take course 0. So in this case, we can just return true. Pretty much when we want to complete this problem, we want to make sure that the graph is acyclic, right? We want to make sure that the graph is not cyclic. And to do that, we basically have to sort the graph using topological sorting. And then at the end, if there's still more edges, right? If there's still edges around, then we know that this is a cyclic graph. Then we can just return false. That means that we cannot complete all the courses. So to solve this using topological sorting, and notice that the question is not asking to return the sorted version, the list of sorted nodes, right? We're not looking to sort the nodes. We're looking to see if there's a cycle in the graph. We're looking to see if we can complete all the courses. And what we can do is we can do exactly what we talked about, how we can solve this problem using topological sorting, right? We can basically have a result list, not result list, but sorry, we can have a hash set that keep track of all the nodes that has no incoming edges. And we can also have a table that keep track of each node's edges, right? So that we know that how many edges this node has, and this node has no edges at all. If it does not have any edges at all, we can just remove that, right? So that's what I did here. And here you can see we have a graph, right? So we have course 0 is the prerequisite of course 1, right? And then course 2 is prerequisite of course 1, and then course 2 is a prerequisite. Course 1 is a prerequisite of course 2, and then course 2 is a prerequisite of course 3, right here. And then all we have to do here is we're going to have a table to keep track of all the incoming edges for each and every single node. And you can see that 0 has no incoming edges, and node 1 has 1 incoming edges, and node 2 has 1 incoming edges. And then we're going to have a table that keep track of that add all the no incoming edges element onto the hash set. And then what we're going to do is we're going to get all the nodes in the hash set to delete all the connections to other nodes, right? And then once that node has no connection, we can just remove that off the hash set. And then basically at the end, we also have to make change on the table. And if there is no connections at all, if there's still more connections, right, we're going to return false. If there's no connection at all for each and every single node, that means that this is not a cyclic graph. Then we can just return true. So here you can see what we're going to do is we're going to first adding all the each and every single nodes and their connection, right? Then what we're going to do is we're going to remove the node that we're going to get the node that has no connection, no incoming connection, no incoming edge onto the hash set. Okay, and then what we're going to do is we're going to remove an element off of the hash set, and what we're going to do is we're going to delete all the connection that this node has, right? Node 0 has a connection with node 1. We're going to delete that connection by saying that, okay, we know that node 0 is the prerequisite of node 1, then we just have to decrement this node 1 incoming edge by 1. So now node 1 incoming edge should now be 0, right? Because 1 minus 1 is 0. And now what we're going to do is going to remove 0 because this node has no incoming, has no connection, no edges at all. So we can just remove that off of the hash set. And then what we're going to do then is we're just going to getting the next node that has no incoming edge onto the hash set, node 1. And then node 1, in this case, you can see has 0 incoming edges. Then what we're going to do is we're going to delete all the incoming, all the edges that node 0 has. In this case, we're going to delete this one, right? Node 1 is a prerequisite of node 2, and 1 minus 1 is 0. And then we're just going to remove that element off of the hash set and adding 2 onto the hash set because 2 has 0 edges, right? So, 0 incoming edges. So we're going to take 2 out, and then we're going to say if there's any connection that 2 has, right? In this case, 2 has a connection with 3. Then we're going to decrement this by 1. And now 3 has no incoming edges. Then what we're going to do is we're going to add 3 onto the hash set, and then we remove 3, and then what we're going to do is we're going to see if 3 has any connection. In this case, 3 has no connection. Then what we have to do is we're just going to return true because in this case 3 has no connections and there's nothing. We basically do a loop to check to see if all elements in the table is 0. Then if that's the case, then we can just return 0, and because the hash set is empty, right? And if the hash set is empty, that means that there's no more elements that 3 is connected to. So let's take a look at another example where we have a acyclic graph. Okay, so what we're going to do is we're going to first get all the connections that 0 has. In this case, 0 has 0 incoming edges. Then we're going to add it to the hash set. Then what we're going to do is we're going to see if we're going to break all the edges, all the connection that 0 has. In this case, 1, right? We know that 0 is connected to 1. Then what we're going to do is we're going to decrement the number of incoming edges that 1 has now is 1. And then if this node that we're deleting, if the incoming edges does not equal to 0, then we don't have to add it to the hash set. So in this case, we know that the hash set is now empty because we delete it. We basically traverse all the connections that 0 has and delete that connection already, like we delete this connection already. Now 0 is gone, right? It has no connection. Then we basically do a for loop to see if there is any ones, right? If there is any still edges going on. We realize that there's still edges going on, right? There's still 1 incoming edges for 1. Still there's 1 incoming edges for 2 and 3. So in this case, this is an acyclic graph, so we're going to return false. And we cannot be able to complete all the courses. So now you know how we can do this. Let's try to do this in code. So our first step will be to creating this array, right? This table that keep track of how many elements, how many incoming edges this current course has, right? So what we're going to do is we're going to have a table. You can use a hash map or hash table. I'm just going to use an integer array. So we're going to have a size of num courses, right? We have num courses, and in this case, what we're going to do is we're just going to iterate for each and every single courses, right? For each and every single courses, right? Prerequisites. We're going to get the current course, right? The current course number is equal to courses at 0, right? This is the current course number, and to get the number of incoming edges or number of prerequisites does this current course have, we're just going to look at the first course, right? We're going to see if there's a prerequisite for this course, then we're going to increment that element in the table by 1, right? So in this case, I'm going to say table at current course plus plus. So we're just going to increment that by 1. And then we're going to have a hash set that basically keep track of the elements that has no incoming edges, right? And then for each element in the hash set, for each element, we're going to first find the element that has no incoming edges by simply iterating the table, right? So integer I is equal to 0, or I should say, yeah, in this case, what we're going to, so integer I is equal to 0, I is less than the length of the table, dot length. And what we're going to do is we're going to see if the current number is equal to 0. So if table at I is equal to 0, then we're going to add current index, the current course, onto the hash set. So hash set.add I, right? So then what we're going to do is we could have a situation where there is no edges at all, where there's no incoming edges at all, right? Then we know that this is a cyclic graph. So if the set is empty, that means that we have cyclic graph. So what we can do is if hash set dot is empty is equal to true, then what we're going to do is we're going to return false, okay, because we cannot complete it because there's a cycle. Okay, so that's kind of like our base case before we start. And what we're going to do is we're going to say while hash set is empty is equal to false, right? while the hash set is not empty, then what we're going to do is we're just going to continuously perform the topological sorting, right? So in this case, we're already getting elements that has no incoming edges onto the hash set. Then we're going to start to remove an element off of the hash set. So what we had to do is we had to turn it into an iterator. So iterator is equal to hash set, or I should say hash set dot iterator, and then we're going to have an integer element is equal to iterator dot nest. This will give us the nest element. And then what we're going to do is we're going to take this element, because we know that this has no edges, we're going to get all the elements that has a prerequisite is equal to the current element. We're going to pretty much delete that. We're pretty much going to, in the table, we're going to delete the edge. So we're basically getting all the edges that this current element have and delete it, right? So what we're going to do is that we're just going to call this remove method, because in this case, what we're going to do next is we're just going to iterate the entire prerequisites, right? In this case, we're going to iterate each and every single element. If we found a prerequisite that is equal to current element, what we're going to do is we're going to delete that connection. We're going to delete this this course as the prerequisite of the current element, right? So integer course, right, is equal to 0. So while course is less than prerequisites dot length, then course plus plus. Okay, so in this case, what we're going to do is we're basically going to remove edges that element has, right? Remove the edges that the current element has. And then basically, to do that, we're going to see if there is a situation where the prerequisite at the current course, right, at the current course, the prerequisite is equal to the current element. So check to see if prerequisite is equal to the element. If that's the case, then we found a connection that the current element is connected to. Then we're going to decrement that in the table. Okay, so if element, sorry, yeah, if prerequisites at current course at 1, which is a prerequisite, right? So in this case, the prereq if the prerequisite is equal to the current element, then we know that we found a connection. We found a connection. If we found a connection, what we're going to do is we're going to remove that element, right? We're going to remove that element in the table. So table at, in this case, the current course. Let's do it inside the if condition. So in this case, the current course is equal to prerequisites at current course at 0. That's going to be the current course. So we're going to say the current course, we're going to remove that incoming edges. Right, we're going to decrement by 1 so that we can remove the incoming edge. The incoming edges of this current course. And what we're going to do is that we're going to see if there's still any incoming edges. If there's no incoming edges, we can add the current element onto the hash set. So if table at current course is equal to 0, then what we have to do is we're going to add the current course onto the hash set. So hash set dot add current course, right? And then that's pretty much our job. Is we're going to continuously do that until we remove all the edges of the current element, and adding the elements that has no incoming edges during this process onto the hash set. And then because we already traverse all the elements, what we're going to do then is we're just going to say hash set dot remove element, because we done our job, right? This element is done, we done traversing this element. Then we can just remove that element off the hash set and move on to the next element. Now then, what we're going to do is we're going to focusing on do an iteration, do a for loop, and try to see if there's any edges, right? Because at the end, the hash set is going to be empty. If the hash set is empty, then we know that our job is done. We're going to see if there's still more edges, right? If there's still edges going on, then we know that there's a cycle in the graph. So check if there is cycle by simply do a for loop for each and every single course in the table, right? And if the current course is bigger than 0, then we can just return false. Otherwise, we can just return true because in this case, there's no more edges, right? So let's try to run the code. Okay, let's try to submit. And here you can see we have our success. So basically, this is how we solve this problem using the topological sorting. So the time complexity in this case is going to be big O of V plus E, right? V is basically the vertex and the E is going to be the edges. And then the space complexity is also going to be the same. So now let's take a look at another question. So this question is very similar to the course scheduling 1. Basically, we're asked to perform topological sorting, just like this one, where basically we want to know the order of courses that we need to complete all the courses, right? So if there is no way to finish all the courses, then we're just going to return an empty array. And then if there is a way, we're going to return the array. In this case, if we have a course like this, where the prerequisite is 0, and we have course 1, so in the order is going to be 0, 1, right? So and so on. If there's empty, we're going to return the course 0 in this case, right? So pretty simple. It's very similar to this course, this problem. So I'm just going to copy the problem code here, and all we're going to change is going to change the way how we return things. We're going to return an integer array instead of Boolean. So in this case, what we're going to do is we're going to return a new integer with empty elements, symbol as empty array. Okay. If we have a situation where the hash set is false, right? So if hash set is false, then we can just return. In this case, we can just return empty array. And now, if we have a situation where we found there's a cyclic graph, then we can just return a empty array as well. And then what we're going to do is we're going to have a result, right? Basically stores each and every single element onto it. So basically what we're going to do is we're going to pass in the number of courses as the length. And then we're going to have an index that keeps track of the current index of the result. And then after we remove all the elements, all the edges of this element, we're just going to add it onto this result list. So result at index is equal to current element. Then what we're going to do is we're going to increase the index by 1 for each and every single iteration. And at the end, we're just going to return the result. So now if we were to run the code, new statement, so we should have a return. Return empty array, right? And let's try to submit. And here you can see we have our result. So this is how we solve this problem.